that property. So the property of density is intrinsic to matter. In other words, markers have a certain density, this box has a certain density, feathers have a certain density, lead has a certain density. It's like an ID of the substance. So with density, we can actually identify and differentiate gold from lead or from aluminum. And density is abbreviated as D, at least in this class, capital D, and defined as a ratio of mass to volume. Now, as you can imagine, the units of mass can be pounds, can be kilograms, can be grams, and the units of volume can be milliliters, can be ounces, can be gallons. The proper units of density for chemistry are going to be either grams per milliliter or the exact equivalent, grams per cubic centimeter. So either of those two units for density are acceptable. Now, one thing that is probably good to remember is that 1 cubic centimeter is equal to 1 milliliter. That's why they are interchangeable. And that there is another name for the cubic centimeter out there that you may actually encounter if you work in the allied health field. And that's the cc. So cc is just another abbreviation for cubic centimeter. Could you see grams per cc? Yes, you could, but not here in chemistry. All right? Now, would it be wrong to talk about density in terms of kilogram per liter? There's nothing wrong with that. It's just not the common unit of measurement. Now, how do we calculate density? Well, simply by collecting the mass of a substance, dividing that mass of that substance by the volume that that substance occupies, that sample of substance, and then doing the arithmetic, dividing the two. Now let's take a look at how it's done in the lab, including this lab where we're at. So measuring the mass is actually quite simple. So scales are used for measuring mass. Typically in grams, although there is a button to change the units, although we don't never ever touch it. And then it contains some button called the tare button. There's a tare function on every scale. And the best way I can describe to you the tare function is, I may have said this before. Did I use the example of the airport expensive balance or scale to weigh your luggage so that you don't have to pay the airline for extra luggage? If you have never traveled by plane, airlines impose a limit on how much you can carry on your flight. And after that limit is reached, you have to pay sometimes, quite a bit of money, $50, $60, whatever. That's too much for me. So being cheap, I try to weigh things before so that I don't get surprised. But many scales in many airports, you have to pay to weigh things. And I don't want to pay twice. If I have two pieces of luggage, I only want to weigh them once, not twice. So this is what I do. In fact, I'm tearing in a way, so that will hopefully explain to you the idea of tare. I put one suitcase on the scale, I see the weight, I remember the weight, and then I add the second luggage. The weight goes more. So what do I do to find out the weight of the second one? I subtract the first weight from the total weight, and that gives me the weight of the second suitcase. Does that make sense? That's staring. So if I want to measure something, let me very quickly, this one will do. Oh, I'll do a smaller one. If I want to measure something in this beaker, and I put the beaker this is reading 0, and now I put the beaker there, and now it reads something because this weighs something. If I hit the tare button, it's going to zero the balance. So that way, whatever I put in here is the weight that I'm measuring. If I don't hit the tare button, I'm going to have a weight there that I need to write down, put the marker or whatever I'm weighing, write that second weight down, and then subtract the two, just like I did at the airport. So the tare button is very handy. However, in one of the experiments that you're doing online, virtual, they don't use the tare button, and you're supposed to use a mathematical formula to take care of that tearing for you. So I'll explain that in a few minutes when we look at the lab. So that's the tare function. Now, let's say that we want to get the density of this marker. So I need two pieces of information. I need the mass and I need the volume. The mass obviously is simple. I use the scale, I put my marker on, and I have a number. And let's say that I get something like 52 grams. I'm done with the mass. How do I get the volume of this? How do I measure the volume? This is a nut-shaped object, right? It's not exactly a cylinder. It has a strange shape. Let me backtrack and ask you, this is more of a cubic object. How do I measure the volume of this box? Yes? Say that again.
Length times width?
Yes, length times width times one more thing. So let's call this the length. No, well, that's the width. Well, that's the width.
Oh, wait,
So there's three. Yes. So there's three things that you need to measure. If you only measure two things and multiply them, you get the area. If you want the volume, you need to measure three things: the length, the height, and the width. So length times height times width. For a cubic object. But this is not cubic. This is more like a cylinder. And there is a formula for a perfect cylinder. Something like 4 pi over r or something like that. It doesn't matter what it is. There's a better way. That better way uses a graduated cylinder. And let's just do the thought experiment, since that's the way we're working. I'm going to draw a graduated cylinder here for you with an imaginary 40 milliliter volume maximum. And each 10 milliliters have 9 little lines, like so. 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. And if I want to measure the volume of this object, like the marker, this is what I can do. I can put some water here and record the volume of the water. So in my imaginary experiment here, that's 10, 11, 12, 13, 14 milliliters is the volume of H2O. Okay? Then I get my object that I want to calculate the volume of, and I drop it in there. Now, of course, I am assuming that this is going to sink, not float. If it floats, that doesn't work. But let's assume that this sinks to the bottom. So the marker sinks to the bottom. Now I have my marker there with the cap. And what do you think is going to happen to the amount of water?
It's gonna rise.
It's going to rise. And it's going to rise proportionally to the level occupied by the volume of the marker. So let's say that this goes up to 28 milliliters volume of H2O plus marker. So just like the third button, except that this is for volume, what do? I subtract the volume of the water by itself from the total volume. So 28 minus 14, oh my, I get 14. I should have used a different number. Well, it is what it is. 28 minus 14 is 14 milliliters. That's the volume of marker. And this is known as measuring volume by displacement. So we just measure volume by displacement. It really beats trying to use math, geometry. There's no use of a calculator except for the subtraction, and you have the volume of this marker. So if that is in fact, in my example, the case, I put 14 milliliters on the bottom, then we just do the math. So if you don't mind, please calculate that imaginary density, and let's put it with the proper units. So what is 52 divided by 14? 3.714 grams per milliliter. Now let's take a look at that number. In my example, both of these numbers have two significant digits. So my answer has to have two significant digits to be properly written. So I will drop the 1 and the 4, keep the 7, and that's what I would report. 3.7 grams per milliliter is the density of that imaginary object, marker, or what have you. So that's how you calculate density. Yes?
What is the 52 grams? Is that the 20?
That's the weight of the marker. So that's why I got by putting that on a scale.
So we added the 20 and the 14?
Right. So these are two different measurements. Mass is measured on a scale. Once we're done with the mass, we forget about that and we proceed to calculate the volume, which is the second unit of measurement that we need to get. We did that with this imaginary experiment. We had a graduated cylinder with some water, nothing else. We recorded the volume of the water. We added the object that we want to measure its volume. The level of the water went up proportionally to the volume of the object. And then we subtract. Yeah, I hated that I used the same number. Let's say that this was 30 milliliters. It's over there. It's just an imaginary object. So now we subtract the 2 and we get 16 milliliters. And of course the answer is going to be different, but we're not going to go there. Does that answer your question?
I was just wondering where the 52 grams, I didn't know if we were adding those numbers together?
Right.
Okay.
Yeah, we are not. These guys are a different measurement from the mass measurement. This we were done with in the scale. We check it as being done. Now we're working on getting the volume, this second entity. That second entity was obtained by this imaginary setup. And then you record that volume there, and you have a way of calculating a density. Now, with a little bit more practice, it's probably going to be more clear to you. So let's just do a couple of problems here, maybe from the homework. Let me see if I can find, because this last problem from the homework is going to be really a challenge. So here I have a problem on the screen. Oops, what did I do? I'll turn on the projector, but I'm going to just put the data on the board, just so that you know that this is coming from the homework for chapter 2. Can I erase this information? Is it okay? Okay. Now, please don't forget what I said earlier about density. Density is a property of matter that allows you to identify matter. It's like a social security number. It's only associated with one individual, or your fingerprints. Your fingerprints are only yours. The density of gold is only the density of gold. No other element has the same density. Okay. Now the problem from the homework asks to determine the density for each of the following. So we have several parts. We're going to calculate the density for each of these examples.
Would this be the same map that you were just showing us on the board?
It changes with every problem.
I'm saying
Oh.
like the numbers change, but I'm saying like the formula
Is the same.
Is the same.
Yes. Unless they're asking for a different thing, which we'll see.
Yeah, in regards to density.
Okay, great. No. So the formula is the same. Let me put it here. Density equals mass over volume. That first example has a car battery fluid with a volume of 125 milliliters and a mass of 155 grams. So that's the sample. Okay? So all we had to do is input these two numbers into this formula. Of course, in the proper place, mass has to go on the top, 155 units of grams. Volume, 125 units of milliliter. And now let your calculator do the work. And the problem does ask you to use 3 significant figures. It's not asking you the proper number, it's asking you for 3. They happen to be the same. We have 3 and 3. So what do you guys get? I need 2 answers that are the same so that I know that we're doing this correctly. 1.24? 1.24, perfect. Grams per milliliter. So let us enter that in here. The units are given to you, so we just need the numerical part. And I'm going to submit that answer. It gives you feedback about the answer. So that's always good to know. Okay, so here is a second problem. So here's a second problem. They want you to calculate the density of a plastic that has a mass of 2.73 pounds, lb pounds, and a volume of 3.6 liters. So let's be careful. They want the density in grams per milliliter, which is what I told you is the normal way of getting density in chemistry. But the information given to us is in pounds and liters. So what do we have to do? Do I go ahead and put 2.73 here and then 3.6 on the bottom? I could, but the units are going to be pounds per liter. And that's not what the answer wants. So we need to convert. Even before we can do the calculation and then do the conversion, but it's easier to just convert these two individually and then plug the right numbers. So let's do the mass first, because that goes on the top. So we have 2.73 pounds, and we need to convert them to grams. Now, different sources are going to give you different conversion factors. I'm just going to go with an easy one, 454 grams to a pound. Okay? If you Google it right now, or if you search the internet for it, it may say 453 point something something. Let's just go with this equality. 454 grams are equal to 1 pound. I didn't invent that. This is a known fact that you had to research, and you need it. I know that you can probably ask a smart speaker, Google, Alexa, Siri, whatever, how many grams are in 2.73 pounds? And please do it. There's nothing wrong with it. But if you don't have access to one, or if you just want to learn how you do it the chemistry way, we need to multiply these by a conversion factor that comes from this equality. Two possibilities, 454g over 1 lb, or 1 lb divided by 454 grams. So those are the two conversion factors that come from that equality. Every equality yields two conversion factors, always. And they're always ratios. Then you need to choose. You need to choose which one to put here that, when multiplied, cancels pounds and leaves you with grams. As I have said earlier, you always choose the one that has the units that you want to keep at the end on top. So I'm going to choose this one because g's are on the top. So 454g divided by 1 lb. Whatever that gives me is my amount in grams equivalent to 2.73 pounds. So can you do that with your calculator? And let's leave it at 3 significant digits. Two answers that match.
So you just want us to multiply 2.73
You're multiplying this by that,
times, okay,
which means
divided by,
you multiply by 454 and divide by 1. So when I say multiply, air quotes, this is a fraction. So if it were the opposite, you're really dividing by 454, right? You need to be careful about that.
so that will give me 1,239.42.
Okay? And the units are grams. Let's reduce these to 3 significant digits. So that means we need to keep the 1, the 2, and the 3 and drop that. This is a great way to practice rounding off complicated numbers. What is this number in 4 significant digits? I mean 3 significant digits.
123.
Well, we have a problem there.
Couldn't you remove the decimal, please, and make it
Remove.
actually round the 3 up to a 4 and make it like, no, never mind.
We need 3 significant digits. I mean, I could round it off to 4. You're right. So this number rounded up to 4 is going to be different than to 3, but it's going to be roughly the same. Thank you for that point, by the way, because that's going to clarify some things. We'll do that in a minute. So, yes.
Oh, I was just wondering if you have to simplify, or I mean round rather, the .42, either, I mean the ones place, the 9.
Right.
If you have to round that up or down based on the decimal, what's right of the decimal.
Right. So if
I wasn't sure I was asking.
let's take a quick detour here, and let me put the number there. That number has 6 significant digits, right? What if I were to ask you to reduce that to 4 significant digits? I want to keep that, and that. I want to get rid of those 2. What would you say the answer is?
The same thing, 1, 2, 3, 9.
Exactly. 1, 2, 3, 9. No period. I mean, I can put the period, but there's nothing after that. That has 4 significant digits. But what if I want to reduce this number to 3 significant digits instead? I only want to keep the 1, the 2, and the 3, where I was told that 1, 2, 3 would be the answer.
So that's not a problem.
That's not a problem?
It's fine, right? That's the correct answer.
No, it's not the right answer because it has a big problem. The big problem is that this is 1,239. This is 123.
So we just have to.
This is 123. It's 10 times smaller. We made a huge mistake. So the 0 is the magical placeholder that has no bearing in the number of significant digits. So what happens if I just put a 0 there?
It's still 3 significant.
It's still 3 significant digits. As long as I don't put a period there, because then that makes a 0 significant. So that 0 is just basically telling me, you have to be in the 1,200s. You cannot be 120. That's a huge difference in dimension. So the 0 is a placeholder, not a significant digit. That's how you do it. It's not 4. Well, it has to be 4 actually. Because this is a 9. So yes, this has to be a 4. Because you drop the 9, meaning this has to go up by 1. So 1240 is better than 1230. I mean, both are numbers with 3 significant digits, but this number is closer to that number than this number. This number is half a unit away. This number is 9 units away. So that's a better rounding off. So thank you. You were right. This is the number we need. And we got lucky because of that challenging number going down to 3 significant digits. So does that make sense?
Yeah.
Okay.
I just wasn't sure if you had to round the decimal up or down first. That was my only question.
Okay. So the decimal tells you the size of the number, so it has to stay in place relative to the size of the number. I cannot round 1,000,000 to 1,000. I can round off 1,000,000 to 999,000 or vice versa, right? Okay, so now we have the amount of mass in grams, and I'm going to put it right here. We're done with that, 1,240 grams. And now we are left with the bottom, the volume. The volume is given in liters, so we also have to convert it. So I'm going to erase this previous conversion, and we're going to need a different conversion factor. What do we know about the liter? That 1 liter, and again, you can look this up. You don't need to memorize them. Equals to 1,000 milliliters. Exactly. So from that, we have 2 conversion factors. Either 1 liter divided by 1,000 milliliters, or 1,000 milliliters divided by 1 liter. Those are my two conversion factors that come out of that equality. My conversion is 3.6 liters, which I need to multiply by one of these two. But I need to keep milliliters at the end. So I'm going to choose the conversion factor that has milliliters on top. This one. Otherwise, I don't get milliliters. So I put 1,000 milliliters divided by 1 liter. And if I carry out this operation, liters and liters cancel because they are on top and the bottom, top and bottom. And I end up with, this one I can do in my head, believe it or not. I hope I did. 3,600 milliliters is the answer. Always do it on your calculator to make sure. Yes?
So what do we cancel out?
We cancel out liters with liters because, okay, so this number doesn't have a denominator, right? But it does. It's an imaginary one. This is divided by 1. We don't write it because that's the convention. So these liters is on the numerator, and these liters is in the denominator. So that divided by that is 1. So that's why we say we cancel them.
Okay.
Okay? Okay. So now we have the second number in the proper units, 3,600 milliliters. So can you please do that division, and let's report the answer to two significant figures. That's what they want. Which if you...
0.34.
0.34? Same thing? All right. 0.34 grams per milliliter is the density of that. That's a very light plastic. The smaller the density, the lighter, on quotes, the object. Because light implies weight, but we're talking about density. Okay, so that's two significant digits. Let's see if my only worry is that I use the 454 grams to a pound, which may not be exact. Let's see what happens when we enter the answer. 0.34. God, I can't see. 0.34. So we got it right. And they did exactly, oh, they used 454. That's why we got it right. If you Google or search the internet, you may have a slightly different number. Please don't panic if you get a problem wrong. I can always fix those all the way to December with absolutely no worries, okay? Yeah, so all you have to do is tell me. I hate my grade. I deserve higher than that. I'm not going to argue with you. I will just ask you to confirm that you know why the wrong answer that you get is the wrong answer and we should get it right. Or you may discover a mistake in the book or in the website. Mistakes can happen. Okay? All right. So there's one more and then we can move to the nasty one, which is the one that is going to bring a closing to the chapter 1 and 2 very quantitative material. Chapter 3 is a little bit more descriptive, meaning there's less math than in this one. Okay. So, next problem. This is a urine sample with a volume of, I think that's a decimal point. So that's interesting because that's what is going to give us the 4 significant digits. That number has 4 significant digits because of the period and the zeros after. Those are really telling us the real volume. So we have a 4.000 milliliter sample of urine, 4 milliliters, and it has a mass of 4. Oops, I put it wrong. This is the volume, 4.000 milliliter sample of urine with a mass of 4.009 grams. Oh, thank goodness. We don't have to do any conversions this time. We have grams and we have milliliters, so we're just going to put the numbers. Mass goes on top, 4.009 grams. Volume on the bottom, 4.000 milliliters. And what do you get? 4 significant digits. That's the hard part of this one.
0.99.
0.99. So that has only 2 significant digits. Is that what your calculator is giving you? No more digits?
I'm sorry, I was doing one.
Oh,
That's a different one.
so why is somebody else getting?
Oh yeah, it's actually the same thing.
So 0.99 and there's no more digits.
I guess it's
7.
different.
What did you get?
I got 1.00225.
Okay, we have a 1.0025.
No, two twos and 1 5. Just another 2.
Like that?
Yeah.
Okay, so do I have another person getting a 0.99? Do I have another one of you guys getting a 1.00225? What are you getting? Dividing that by that.
Because I divided different. I divided the opposite side. Yeah.
Okay, so
I got this 65.
you got the 1.00225, okay? Okay, so let's put it up here. And now let's fix the number of significant figures to 4. So counting from the larger part of the number, 1, 2, 3, 4. We need to drop those 2. That 2 tells me to keep that 2 as it is. I don't have to increase it. So now the answer is 1.002 grams per milliliter. That has 4 significant digits. That's the answer. So 1.002. I better be ready. Okay. Now when you go back and if you haven't done the work and you haven't finished it, when you go back to work on it, the numbers are going to be different. The computer scrambles them and it generates a new problem every time. Okay? Okay, so I'm not going to do that last one, although you can see that we also had to make a conversion of pounds to grams. The milliliters are going to stay put. I think by now you know what is going on here. However, what we will do is I'm going to see if I can find a problem in which you have to find the mass given the density or the volume, or find the volume given the density and the mass. That's another possible problem. Oh, this one was, I did this on Monday, so we're going to do it. It's a little bit of a challenge. This one is a little bit of a challenge, but let's leave this for last?
How about a 35?
35, that's the long one. That's the really difficult one. Are we going to do that last? I mean, at the very end, that's the one that I was talking about being super long and complicated. Okay. Let's do this one just because it talks about measuring volume by displacement. And then we'll do one more, the one that I'm trying to find. So we have a problem in which we are told that you have a gold nugget with a mass of 521 grams. And we're not given the volume, we're asked the volume to be calculated by displacement. So they have the mass of the gold nugget is 521 grams. The volume, we don't know yet. So let's do the imaginary experiment. We have our graduated cylinder, the volume of the water, the initial volume of the water is 50 milliliters. Then you drop the gold nugget with an odd shape. The level of the water goes up to 77.0 milliliters. I'm going to call the initial the 50 and the 77 the final. What's the volume of the gold nugget? What do? We subtract 50 from 77, right? Volume of gold nugget equals to final volume minus initial volume, 77.0 minus 50.0, 27.0 milliliters. Does that make sense? The volume of the water went up proportionally to the volume of that gold nugget. So, volume 27.0 milliliters. Now we do the calculation. So, mass 521, volume 27.0. What do we get? Yes?
Well, I have 19.29, and then we're gonna, so 19.3.
19.3 is what you got. Perfect. Is there anybody else who got 19.3 or thereabouts? Rounded off already. Thank you for the proper number of significant digits. So 19.3 grams per milliliter. This is a multiple choice one, so let's see if that answer is here. Oh yeah, it is there. So 19.3. Good. Let's submit it. And we got it right. No feedback this time. Okay, let me see if I can find one with mass or... No. These are all conversions. Okay, so I'm going to have to invent one here. Let's just make one up. So far in our discussion of density, we have had problems in which we are given a value of mass and a value of volume, and we're asked to calculate the density. But what if we had a scenario like this? Let's say that you were given a sample that has a density of 1.092 grams per milliliter, and you are told that you have a mass of 45.2 grams, and you want to discover the volume of that sample. So you have the density, you have the mass, but you don't have the volume.
You can multiply the two to get the volume?
Well, let's see what we have to do. We know that this equation is correct. Density equals mass over volume. Here we don't have the volume, so we need to somehow have an equation in terms of density and mass that gives us volume. So we rearrange that formula. I'm going to rearrange it two different ways so that you see that there's two formulas that can come out of that single formula. I could rearrange it so that mass is by itself on one side of the equal sign by doing some magic, and that would be density times volume. Just like that. Please don't ask me to show you how to solve the equation because, although I can show you, that's your arithmetic that you should try to remember. If you cannot remember it, then just copy that formula and have it somewhere available. Now that one doesn't help because we have the mass. We need another formula coming from here in terms of volume by itself. So that comes to be this. Volume is equal to mass divided by density. That came from that equation, just as this one did. Now we have three choices. Obviously this one has the one that we need because we have the mass and we have the density. We need to find the volume. So we're going to use that formula to answer this question. The volume of this sample with these two characteristics is going to be 45.2 grams divided by 1.092. Now let's look at the units. These are a little more complicated.
Sorry to interrupt. What number is this here?
There's no problem in there. I made it up. I invented
Just
it.
made that up. Okay.
Yes, I couldn't find one, so I made it up. So numerically, this is going to give us the answer that we want, but we're going to have to think a little bit about the units. This top number has a divided by 1 imaginary that you don't see there, right? So these are like this. Grams divided by 1 divided by grams divided by milliliter. When you have a scenario like that, this guy cancels this guy. And the units that we remain are milliliters that go on top. And again, please review that on your own if you don't know where that came from. But that and that cancels out. We are left with milliliters. It has to do with fractions. And you may have to go back and review fractions and the rules. But numerically speaking, what is that? What do you guys get?
How many significant digits?
Well, let's do it by what we have here. We have 3 on this one and 4 on that one, so 3 significant digits.
Rounded off, it would be 41.4.
41.4 milliliters is one answer. Can I have a confirmation of that number? Is there somebody else getting that same number? Okay, so we are good. So what's the message of this last problem that I couldn't find one in the homework? There may be one in the quiz, I don't know. But that whenever you have a formula with 3 variables, you always need 2 pieces of information to get the final one. In most of the problems that we have done up to this point, we had the mass and we had the volume and we needed to find the density. So we had 2 out of the 3. In this last example, we have 2 out of the 3, but the one that we're missing is the volume, so we needed a different formula, which is still related to this one. They are all the same, rearranged in arithmetic. Okay? Okay, so now, before we do problem 35, which is really going to be a challenge, let's take a look at the other one that I did happen to solve on Monday. Actually, I feel like I was put on the spot because I had not seen that problem before. And when I first saw it, it's like, oh my God. Well, actually, 35 is also pretty challenging. Even for a professor. Please don't get me wrong. I get intimidated by this stuff just as much as you do. It's not second nature. It's you have to think about the stuff. But if you take a deep breath and take your time, most of the time you can actually find an answer. There. So in this problem, we have a new type of measurement that we haven't seen before called the PPV. Okay? What if I were to write something like this, PPH? Does that mean anything to anyone? What on earth is PPH? Oh God, I don't know. What is PPM? And what is PPB? Well, this one I made up. I don't think you will ever find it. However, it means parts in my imaginary world per 100. In other words, that's percentage. Percentage is parts per 100, right? Percent per 100 equals to percentage. I actually left one out. PPT. PPT has a symbol like this, parts per 1,000. So don't worry about that one, but that's parts per 1,000. ppm, parts per million. I'll put it numerically in a minute. And the one that we see in that problem, as you can guess, is parts per billion. So it's a very small amount. Never mind, you don't want that in your water, even at that small amount. It can kill you. So some chemicals are so powerful that even 1 in a billion particles of that can do harm. So parts per billion. Numerically, parts per million is 1 over 1 million. And parts per billion would be 1 over 1 billion. 1 billion of the US, 9 zeros. 1 part of something for every 1 billion parts of something else. Okay, so now let's see We're going to handle then this problem as parts per billion being just something like percentage. Yes?
What's the upside down H?
Oh, very good question.
I was like,
You mean this one right here?
yeah, that one.
So, what did you call it? An upside down?
H.
That's good.
What is it?
It's a symbol, but it's actually a Greek letter, small case, mu.
Oh, the fancy N.
That's the name of the letter in the Greek alphabet, but we read it as micro.
I
So,
remember you showing us the M last week. So the M is the same as that?
is that an M? Well,
It looks like an M to me, like a fancy M.
yeah, it does look like a, yes. I intended it to write it as a U with a long tail, but M, whatever it means to you is fine by me, as long as you remember that this is the way it looks on the computer, and it means micrograms.
Okay, thank you.
And in this context, you're welcome. Micro means a millionth, okay? So we'll put it on the board very soon. Okay. An upside down H?
Upside down H.
Okay, I'm going to use that as an example later. Okay. So let's put on the board what 3 ppb means. So we have 3 parts of herbicide for every 1 billion parts of soil. What does that mean? Actually, it means 3 grams for every 1 billion grams, or 3 pounds for every 3 billion pounds. So parts can be anything. Okay? Now, we need to make a conversion here of either pounds to micrograms or micrograms to pounds. But the answer is given in micrograms. So what we have to do is convert the pounds to micrograms, so that we are in the same dimension, in the same measurement dimension. So step 1, convert pounds to micrograms. Because that's how much soil we have. So let's do it over here. 1 pound. And here we have the conversion factors that we're going to need. Unfortunately, we're going to need 2 of them. If you remember, earlier we said that 1 pound was equal to 454 grams. Right? We used that in a previous problem. Micrograms is in the metric system just as grams is in the metric system. And the beauty of this is that metric system conversions, simply you multiply by a factor of 10 or divide by a factor of 10. 10, 100, 1,000, 1,000,000, whatever it is. But we still need the conversion factor. We need to know how many micrograms are in 1 gram. So I'm going to put here that 1 gram equals to 1,000,000 micrograms. I'm going to Google that just because I'm not 100% sure. I mean, I am. But so there it is, 1,000,000. I better count them. 1, 2, 3, 4, 5, 6, yes. So 1 gram is 1,000,000 micrograms. Okay, so we need those two conversion factors, those two equalities. Remember that from every from every equality, you get two conversion factors. So the very first thing that we want to do is multiply pounds by something coming out of here that would eliminate the pounds and leave me with grams. So we want the grams on top. So we're going to say 454 grams divided by 1 pound. Nothing new. That's how we did it before. Again, please, two conversion factors coming out of every equality. By the same token, this is going to give you 2. 1 gram divided by 1,000,000 micrograms, or 1,000,000 micrograms divided by 1 gram. Those are the two conversion factors coming from that equality. So when we multiply those two numbers, we get rid of pounds, we keep grams, right? Now let's add a second conversion factor that would eliminate grams and leave us with micrograms, because that's what we want, since the answer is in micrograms. So which one has the micrograms on top? This one. That's the one we multiply by. So 1,000,000 micrograms divided by 1 gram. Before I do the math, I want to make sure that the units are correct. So top and bottom cancel each other out. Top and bottom cancel each other out. I'm left with micrograms. We chose right. So now please do the math. 1 times 454 times 1,000,000. We should be using scientific notation, but I'm going to stick with decimal just because I don't want to complicate matters. So my answer is going to be 454 million. Micrograms. Okay? Now, we're ready for answering the question by doing the following. These are micrograms of soil, right? Because we started with 1 pound of soil. This is 1 pound of soil, as per the problem. So now, let's put that number here, 454 million, micrograms of soil. And we want to convert that to micrograms of herbicide, right? We actually have a conversion factor, believe it or not. This is a conversion factor. Let's put it on terms that we can understand. We have it right here. So I can rewrite this. Instead of using parts, I can say micrograms and micrograms. As long as I keep the same units for parts. I mean, it's like percentage. Percentage can have any units that you want. So now I have that equality, and actually, just the way it appears here, I can put it right in here. 3 micrograms of herbicide is what is found in every 1 billion micrograms of soil. But we don't have 1 billion micrograms of soil. We only have 454 million So we need to do that conversion. Looks complicated, but when you go home, please look over your notes in the quiet of, well, if you can find quiet at home, so that you assimilate this information. If the video works, I'll upload it over the weekend, maybe Friday, so that you can suffer my explanation again. But let's do this math. Please forgive me for what I'm going to do, but I'm going to try to save some time here. So this is on the top, so I'm going to cancel these 3 zeros with those 3 zeros, those 3 zeros with those 3 zeros. So now it looks just like 454 times 3 divided by 1,000. That's the way I would do it. Yes?
I just want to verify, so this is step 2 on your ask or convert pounds.
Oh my God. Absolutely. Convert pounds to micrograms of soil, and now convert micrograms of soil to micrograms of herbicide. Thank you for that. Absolutely, thank you. There's a beautiful logic to this. So once again, maybe under the pressure of being in the classroom and trying to finish on a short period of time, it doesn't come to you naturally. I'm a visual learner, so looking at this again on my own may help me understand what's going on. So micrograms of soil cancel with micrograms of soil. 454 million times 3 divided by 1 billion gives me my answer. So what is that?
Would it still be 1 billion because we crossed the zeros out? Would it just be 554 times 3 and divided by 1,000?
Exactly. And that's what I just did here. I canceled the zeros. Yes.
Oh, no, I was just saying, because when you said to the
Oh.
you said 1 billion. That's why I was...
Right, no. So if I want to... Okay, so please, once again, forgive me for maybe sometimes making assumptions that you know what I'm doing by canceling zeros. The reality is that if you don't cancel the zeros, you're still going to get exactly the same answer. So if you multiply 454 million by 3 and divide by 1 billion, it's going to be the same as 454 times 3 divided by 1,000. Same thing. 1.362 is the final answer. Herbicide.